Well, this aims to be the final lesson of your BC course. This may be 2 videos. I haven't figured out how long this is going to take, but there's a lot to cover here because we have to go back over the pre-cal very quickly of polar functions, and then we'll get into the calculus that we're supposed to know dealing with these kind of curves. So let's really quickly go back and talk about polar coordinates and what they mean. So let's say I have a point here in the coordinate plane that has the traditional XY coordinates 2, 2. Let's quickly talk about what that means, because we've grown up now with rectangular coordinates, so we don't really think about them very much. But if we'd explain that to somebody, hopefully you'd be able to come up with an explanation that said, well, that means I have displaced 2 positive units horizontally from a place called the origin and 2 units vertically positive in a positive direction from the origin. Okay, so that would say go 2 units to the right and go 2 units up, or go 2 units up and then go 2 units to the right, however you'd like to slice it. And for most purposes of this course, the rectangular coordinates have been great. We saw in the last couple sections that there are these other functions, parametric functions, that will graph graphs that are not functions in terms of x and y, but are functions in terms of another parameter, and we're going to see a similar thing happen here. Now, this is one way to describe this dot in the plane, but it's not the only way to describe this dot. So let's start talking about a second way that comes in handy from time to time, and is called polar coordinates. So we have rectangular coordinates, x and y, and now we have polar coordinates, which are going to be theta. So we're going to say let theta be an angle in standard position. We'll talk about what that means in a second here. And let r be the displacement from the origin. So my dot now is not going to be measured in terms of horizontal and vertical displacement from the origin. And by the way, the origin is usually called the pole in this context, which is why they're called polar coordinates. We don't really need the x and y axes anymore. I leave them up there just for reference, but in the polar world we only have this dot here, which is called the pole. Alright, now, what is an angle in standard position? Okay, let's review that. Standard position means that I have an angle whose initial side, where it starts, is on the positive x-axis, and its vertex is at the origin. Okay, vertex is at the origin. And let me just adjust this dot so that it's on the angle here. So if I think of having a compass and drawing an angle, where I start drawing the angle is the initial side. So this angle would be drawn this way. This would be called the terminal side, where it ends. And vertex at the origin, I think, is self-explanatory. Okay, so I now have theta defined. All right, and then r is the displacement of this dot from the pole. In other words, how far away from the pole is that dot? So that's labeled r. R could be negative, which just means that you would measure in the opposite direction from theta. So in other words, you go this way. Theta could also be negative, which means that your angle is moving clockwise versus counterclockwise. Okay, in this world, we can relabel this dot with these coordinates, r, comma, theta. In this picture here, how far is r from the origin? Well, we can figure that out. This is 2 units. This is also 2 units, so the Pythagorean theorem says that r is square root of 8, or 2 square root of 2 if you like. And what is this angle theta? Well, we know that in a 45, 45, 90 right triangle, that the angle is going to be 45 degrees, or in the radian world, pi over 4. Okay, so you have a new way of describing where this dot is in the coordinate plane. Instead of in terms of horizontal and vertical displacements, now in terms of its displacement from the origin and its angle from the positive x-axis, angle in standard position. Now, polar coordinates have this interesting nuance to them, which bothers some people, and that's that a coordinate or a point in the plane does not have unique polar coordinates. What does that mean? Well, if I say, what are the coordinates of this dot here with rectangular coordinates, there's only one way to say it. It's 2, 2, right? X, y. There's only one way to produce that point. Polar coordinates, though, that's not the case, okay? Because there are multiple representations for this dot in terms of r and theta. Okay, let's talk about some other ways you could have rewritten this dot right here. Other coordinate pairs that make sense here. Okay, so this is also, well, let's talk about a theta that goes around the circle one full time and ends up in the same spot. Okay, so I would have the same r, square root of 8, but one time around the circle past pi over 4 is, let's see here, 2 pi would be 8 pi over 4, so 9 pi over 4 would be a coterminal angle that would end up in the same position, and it would look the same if I just looked at the finishing spot, but obviously drawing it is quite different. Okay, you could also go backwards. So if I go backward 2 pi, I would end up with negative 7 pi over 4, right? Pi over 4, take away 8 pi over 4. So I could also call that dot square root of 8, comma, negative 7 pi over 4. We could also use this with a negative r value. So let's say I went around the pole to an angle of, what is that? That's 4 pi over 4. That's 5 pi over 4. And then I went backwards, square root of 8 units. So then we could say that that's got coordinates negative square root of 8, comma, 5 pi over 4. And we could make both components negative, right? We could go negative 3 pi over 4, which would get me to this location, and then I could have a negative radius or negative r as well. So negative square root of 8, comma, negative 3 pi fourths. Okay, so the point is there are infinite ways to represent that dot, and that will, from time to time, be helpful, but also may be confusing, so we gotta be careful. There is not only one way to describe this point in the plane. Okay, let's talk about some conversion factors for polar coordinates. So let me again draw a grid here, and let's just put a dot anywhere I like in the plane, maybe up here, and let's label this distance here, this displacement I suppose, as r, and then let's drop some perpendiculars to the x-axis. Let's shade that in a little bit. Let's see here, style, that's what I want. Okay, and we'll color that orange. Okay, so first of all, we know that this could be x comma y, this dot here, and this could also be r comma theta. And we want to be able to, from time to time, convert between rectangular coordinates and polar coordinates. Okay, so here we have theta, here we have x, and here we have y, and this is a right angle. All right, so jumping out at us are a bunch of relationships. Okay, the first relationship we should see is that x squared plus y squared equals r squared. So that relates the x and the y coordinates to the r, the displacement. I'm going to call it radius probably a couple of times. You got to be careful because radii are never negative, but this r can be negative. I should also see that, let's see here, x over r is equal to the cosine of theta. Right? Adjacent over hypotenuse equals cosine of the angle. And generally speaking, we write that as x equals r cosine theta, so that I can relate the x-coordinate to both r and theta. And similarly, the y is going to be r sine theta. And then I think there's one more to look at, and that's that the tangent of theta is equal to the y over the x-coordinate. Okay, so there we have some conversion factors. and some relationships that get us between rectangular and polar coordinates. Okay, so let's do a couple examples, I guess, where we convert between the two systems. So let's look at r comma theta, 2 comma pi over 6. Okay, so let's convert that to rectangular. Okay, convert 2 comma pi over 6 to rectangular coordinates. So how would we do this? Okay, I have the r and I have the theta. I need the x and the y coordinates. So I think these two relationships right here are going to help me. The x coordinate is going to be r, which is 2, times the cosine of pi over 6. Okay, which is the square root of 3 over 2. So the x coordinate of that point will be square root of 3. And the y coordinate is going to be 2 times the sine of pi over 6. So 2 times 1/2, which is 1. Okay, so the xy coordinates of 2 pi over 6, which are polar, would be square root of 3, 1. All right, and let's convert. Probably going to have a hard time coming up with one that is nice, but let's just convert the point, I don't know, -1, 5 to polar. Okay, so these are rectangular coordinates, -1, 5. And we're not going to get nice values here, at least for theta. We need to calculate it numerically, but we can get the r, right? If x squared plus y squared equals r squared, then the r is going to be the square root of 26. And the theta, I need to think about what quadrant I'm in here. So -1, 5 is in quadrant 2. So if I look at this relationship, it would say tan theta, right, equals y over x. So theta is going to be, I would think it'd be the arctan of y over x. Okay, but we'll talk about the problem with that in a second here. Okay, arctan of y over x. Okay, 5 divided by -1. And let me jump to the calculator and show you what happens here. Okay, let me make sure. Okay, I am in radians now. I'm doing the arctangent of -5, right? So let's see here. Arctan -5 comes out to be, now here's the issue, right? This is -1.37 radians. Okay, now think about what quadrant that would be in. -1.5-ish radians would be -pi over 2. So this puts you in quadrant 4, which is not where you're supposed to be. We're supposed to be in quadrant 2. And the reason you're getting this answer is because arctan's range is -pi over 2 to pi over 2. So we need the angle that is got the same tangent as this that's in quadrant 2. And I believe we get that by adding pi. So we're going to check this in a second. Tangent of, so we're going to take that angle, add pi to put it in quadrant 2. Okay, and I'll just double check to make sure that the tangent of this answer is the same as above, -5. Okay, so there we go. So 1.768, we'll say, is the theta that we're looking for here. Okay, so just to make a note of what I did there, a little pre-cal, we had to remember that this is going to give me an angle in quadrant 4 or quadrant 1, but I'm supposed to be in quadrant 2. So to fix that, I added pi. Okay, that's probably not going to come up that often, but just so you know, it could happen.